What's up, Internet Synth Media here, and this is, excuse me, I've got a bit of a cold, so if I'm speaking in a particularly bunged up kind of way, I apologise for that. So, this is part 2 of tutorial 3 for Protoplug. Protoplug, if you'll remember, is the Lua virtual machine in the form of a VST, and that means you just install it, load the VST up into your DAW, and then you can write your own functionality, whether that's audio generation or effects, using the Lua programming language. So I'm doing a series of tutorials from that. I have in the description the links for where you can download it. It's free software. It's very good. It's very impressive, and I think more people need to know about it. So this is part 2 of this tutorial. I highly recommend you go and look at part 1, which will always also be linked in the description, because that's where I've written the first part. This is a simple square wave synthesizer. It has 2 square wave audio frequency oscillators and a third low frequency oscillator that's also a square wave. And in the end of the last video, we'd got it basically droning away. Now in this second part, we're going to add envelope shaping to it. I'm not going to spend a lot of time recapping. Just if you're interested in this subject, do go and watch the first tutorial, and I'm just going to jump right in with the assumption that you've seen and understood that code from the first one. So we're in Lua, here we are. So the first thing we're going to do is we're going to make an ADSR function effect, an envelope creating function. Now an ADSR envelope is what? I've got this handy graphic from Lander. So these envelopes are very, very typical in synthesis. They have 4 stages: an attack, normally called A, a decay, a sustain, and a release. Now the A, D, and the R, the attack, the decay, and the release, are all thought of in terms of the time. So the time of A is how long it takes to get from 0 volume to the maximum volume, which for our purposes will be 1. So let's suppose we have a short attack, meaning it will give us a sharp sort of percussive sound. It'll go boop, right, at the initial. So then we have very little time to get from 0 to 1 here. The attack is short. The second stage of the reason we have 4 stages in these envelopes is because if you think about a synthesizer where you've got a traditional piano keyboard, then you've got 2 important events. You've got the event where the player presses the key or hits the piano key, and then they might hold that key down for a while, and then there's a second event where they would take their finger off it, where they release it. Now the idea of these ADSR envelopes is that the moment you hit the key, the volume is going to go from 0 to max in the time of the attack. Okay, if the attack is fast, it's a sharp percussive boop sound. If it's a slow attack, it's going to be more like a sort of swelling violin or something like this, or a whoa. Okay, it's going to take longer to get to maximum volume. Now the moment it hits this point here, it goes into the decay phase and it starts to fall, or the decay stage, and it starts to fall down again. And again, the decay is simply a time, and it doesn't matter what you're doing on the keyboard. The moment you've got to the top, you start decaying again. It's going to just start falling down again. So that's a way of capturing that initial impact, or the first thing that starts the string vibrating, or the column of air, or you've banged a piece of metal or a wire or whatever. So this part here always has the same time, but you don't fall to 0, you fall to the sustain. Now the sustain is not a time. Instead, the sustain is like the holding volume. So when you're holding that key down on your synthesizer, however long you hold it, once you've gone past this attack and the decay, once the decay stage has fallen to the sustain level, and now the sustain is itself an amplitude level, then it will now sustain, it will just keep holding that for as long as you're holding the key down. So these are time, this is an actual amplitude, until you finally take your finger off the key, which is the second event that happens that shifts you from the sustain stage into the release stage. And then the release is the final dying away of the sound, whatever resonator or extra vibration it had, dying back to zero volume. And that again is a time. So this is the standard ADSR envelope. Attack, decay, both in terms of time, sustain in terms of the volume that it holds while you're holding the key down, and then time again for the release. This is very, very standard. So we're going to make an object that represents and is this envelope. Now, I'm not going to explain how this works because the last tutorial went through this, but you can see we have a function called makeN for ADSR. Those are the 4 values for this. First thing we do is we set up our instance variables with attack, decay, sustain, release. I do this even though we don't really use these very much, but it's kind of a useful mnemonic, I think, to have them. What is important, though, is now these DA, DD, and DR. Now, what I'm calling DA, DD, and DR are the change in the amplitude for each step, each sample point in your attack. DA is in your attack stage. So that's like the gradient of this slope here. It's for every step along, how much does your volume increase upwards? That's the DA. When you get to here and you start falling again, we have a DD. And the DD is for every step along in time, how much do we fall? The sustain, remember, is just a volume, and then the release again is how much more do we fall for every time step here. So we do these calculations during the construction of this object. DA is simply 1 over A. A is the attack time. 1, remember, is our maximum volume. We're treating our maximum volume as 1, so 1 over A is the amount you're going to go up every time step. DD is the amount you're going to go down during the decay phase for every time step, but notice that we're not falling to 0, so we've got to know what this volume difference is. So we calculate that as simply 1 minus S. Remember, S is the sustain value here. So to get the difference between 1 and the sustain, you just subtract just 1 minus that. So that's what we do here. Divide that by the time, gives you the amount it falls. Sustain, we don't care about. And then finally release. So again, that's just the fall from the sustain to 0. So that's just S over R. Again, how much do you fall down each of those? We have an initial volume 0, and we have an initial stage. What stage we're in? I'm going to just number these stages 0, 1, 2, 3, and there may even be some more. Now, obviously, we can change the values of each of these 4 parameters in the envelope even after it's been created. So we have set attack method, we have a set decay method, we have a set sustain method, we have a set release. The first thing I do in all of these, if you notice that in the DA, the DD, the DR, in each of these we're dividing by the amount of time this stage takes. We do not want a division by 0 in our code because that will simply blow it up. So the first thing I do in all the set attack, set decay, set sustain methods is I check that the value we're being sent as an argument is not 0. If it's less than 1, then I just set it to 1, because otherwise someone will send it 0 and we'll get a division by 0 error, which we don't want. Now, again, it's pretty simple. When we set the new attack value, we self attack equals that, and we update the value of dA. Same formula here, 1 over A. Similar for the decay function, we make sure that the time is not 0, and we do this calculation here. At this point, remember, we what was sent as an argument called S there is in the instance variable sustain. So we now do 1 minus self-sustain. Sustain itself is not a time, so it's very simple. We just put the new value in, and release, same principle. Okay, so we've got 4 stages. Stage 0, 1, 2, 3. Attack, decay, sustain, release. Now we need to understand a bit about the transitions, but first things, we've got 2 events. We've got the user, or the player, hits the key on the keyboard, and we have the second event, the player releases. These are MIDI event note on and note off. And how does that work? Well, we've got in this envelope a note on method. At the point we receive a note on, we simply set the self stage equals 0, which is our attack. So we just jump to the beginning of this whole envelope at the beginning of the attack stage when we receive a note on event. Similarly, when we get to the note off event, that means the player has taken their finger off the key. We assume typically we're already in the sustain phase, but maybe we're not. Maybe we're still only earlier on. But we want to basically go to the release phase now, because once the player isn't playing the note, wherever we are, we're just dying away. So on the note off stage, we set ourselves to stage 3. Remember, it's 0, 1, 2, 3. And finally, the function that does all the work, or the method that does all the work, is the next. So the next is, wherever we are, calculate the next output value from this and do any further calculations that are needed. So we've got a kind of if-else-if structure here, several branches of this. If we're in stage 0, okay, we're in the attack stage, so all we have to do is our volume, which is self V. If you remember, V is started at 0, it's the initial volume. All we need to do is increment it by dA, which is that change in volume during the attack stage. Okay, so now all we now need to do is think, have we reached the end of the attack stage, which is, have we reached a volume of being equal to 1 or greater than 1. So we just see if self V is greater or equal to 1, then we've reached the top maximum volume, hit the end of the attack, in which case self stage equals 1. Tell it to go on to the next stage. Okay? And then all we do is this method finishes. We've done our calculation, and we just return the new value of the new volume. So during this phase, every time we call next, we're just stepping one further up and returning that value. And it tests whether we've hit the top and puts us into this stage. Second stage is the same, decay stage. We now subtract the change in volume for the decay, so we're falling down again. And then if we've hit the volume sustained, we've hit the end of the decay stage here, then we're going to go into the sustained stage. Third clause is the same. If we're now in our sustained stage, well, in fact, all we do is we're not changing. Our volume is our sustained volume, and all we do is return it. We don't do anything else with it. Because as long as we're in this sustained stage, then we never change the volume. We just keep on the same level. Now, it's not going to be inside next that tells us to move off of this and move to there. Now, remember, that's happening when we receive the note off method here, at which point when we reach the note off, we automatically go into stage 3, the release stage. Finally, if we're in stage 3, the release stage, then again we're going to now decrease the volume, this time by the value of dr, which is the change over the release. And again, well, if the volume has hit 0, then we go into another stage, we're calling stage 4, and we just return it. Now, in fact, stage 4 is a stage that's not really represented. This is not 1, 2, 3. It's just like the off phase, the off stage, the stage where the envelope is not playing at all. And how do we handle that? Well, whenever we get something we don't know the stage, including the stage of being off, we just return self V again. Whenever we are in this unknown stage, we do nothing except return the V again. I've added this little bit of extra function that called note perm, that puts us into the self stage 5, which basically, it's useful to have an envelope, but perhaps sometimes we would like to run the synthesizer still like a drone synthesizer. So in order to switch off the envelope mechanism and just set it into a permanent volume, there's this thing called note perm to set ourselves into constantly at a particular volume. It puts us into stage 5 again, which doesn't exist, but that means we trigger this clause here, and so just keep returning it and never change. I'm not using this, but this is there for when we want to have some sort of switch between either use the envelope or don't use the envelope. And that's it. That's the object that represents our envelope. This object again is the oscillator is the same as it was before. And now I'll show you how some of the parameters have changed so you can understand what's going on next. So if you remember, we had the oscillators, we had 3 controls for each oscillator. We had the amplitude, we had the frequency, the pitch, and we had the pulse width. So we could sort of slightly change that quality of the sound. Now I'm changing things a little bit this time, so I've reduced that number to simply 2 amplitudes, the relative amplitude of the oscillator 1 and the oscillator 2. And now instead of giving them independent frequencies, I have now simply set this thing called freak ratio. Now what freak ratio is what is the frequency of oscillator 2 as a ratio or as a multiple of the frequency of oscillator 1, because we're no longer going to use a slider to control the pitch. We're now going to take in keyboard events or MIDI events to set the pitch of our oscillator, of our synth. So we don't want to have independent setting of that. All we've got now is simply oscillator 1 is going to take its pitch from the MIDI note it's receiving, and oscillator 2 can be set as some sort of multiple of that. So here, if you see, I've got it set up to be 0.5. In other words, it's 1 octave down. We could set it up to be 2 octaves down, or 2 to be an octave above, or of some other ratio. We can put some other number and get a very bizarre ratio if we like. So we have quite a lot of control here, but it's slightly more restricted because the idea is we're playing this now from the keyboard. So that's all we're currently saying about the oscillators. But now we've got these 4, the ADSR values for the sound, right? What's the attack time? What's the decay time? What's the sustain value? In other words, the volume that it sits at here, which is a number between 0 and 1. These numbers I'm just putting in terms of the number of sample points. That's not perhaps ideal, but it works perfectly well at the moment. So I've kept this simple: attack, decay, sustain, release. Now you might ask, well, what have I done with this, the pulse width? Because the pulse width was our way of getting a slight alterations to the quality of the color of our sound. Well, what I decided to do is I decided to put this also under the control of an envelope. So I've got a second envelope, exactly the same as the first one, which defines how the pulse width shifts from 0 to 1 over the course of the sound playing. And just as in the first envelope, we have an attack stage, a decay stage, a sustain stage, and a release stage. So the idea is to shape this, rather than having a knob to control that pulse width, which might actually still be a good idea. I haven't decided if this is an ideal, but in this version of the synth, I just put that under an envelope control. So in a minute, we will see how that is implemented. So we no longer have independent controls of the pulse width, we just have another envelope controlling how it goes from 0 to 1 while the note is being played. Between 0 and 1 and back to 0 again while the note is being played. Finally, we still have our LFO, and we still have the same three parameters for that: the amplitude, the frequency, and the pulse width. So how does it sound? It sounds like this. Okay, quite harsh and electronic sounding, but it's what you expect. I mean, firstly, it's in tune, which is good. And okay, so we had a short percussive. We'll make this a very short percussive, but we still have a long. Okay, we'll pull the sustain down. Now we pulled it down too short. Never gets very loud. Instead, we'll have a release phase. So we'll take the release down. If I hold it down, it plays. But the moment I let go, now if I wanted to make a longer attack, a sort of more, okay, I'll put that back to 0.5 for a second. So I'm going to make the longest attack I can make here. Okay, it's still not a very long attack. We might choose to make that longer, but you can hear that it's working. Now you can hear if I also make a long decay. But of course, the moment I remove my finger, we immediately go into the release phase anyway. Release stage, sorry. People talk about these as phases, but I try to talk about them as stages because we already use phase to mean that thing that moves through the wave, so I figured it would be confusing. But when I talk about attack, decay, sustain, release stages, or if I accidentally say phase, I mean the same thing in that context. So hopefully this is understandable. So let's just look at the frequency ratio. At the moment I've got this set up where the oscillator 2 is half the frequency of oscillator 1. So it's an octave lower. Let's take oscillator 1 right down. And now you can hear it's much deeper. Right, so we can change the relative volumes or amplitudes, and we could also change the frequency ratio. If I made that 25 now, oscillator 2 is 2 octaves below oscillator 1. And oscillator 1 is responding to the keyboard. Or we can pull that up and pull that down. Okay, so that gives us some change in our pitch. Now, we can also change the frequency ratio, right? We could choose something completely arbitrary. And get this rather harsh aharmonic. But sometimes that can be a really nice sound. If you make it slightly detuned, you'll get a thicker sound. And if we were to go right down here, Yeah, so you get a nice thick interference when you have slightly detuned waves here. I will come back up an octave. Right, so let's look at, obviously these, the LFO amplitude, it has the same kind of effect as previously if you have low frequency. If you speed it up, and you speed it up even more, you lose all the sort of tonality, in fact, of your thing. But if you have a mix, maybe at higher pitches, at that point the frequency is too high, it's become its own audio, and we've lost control from the keyboard. So we can get some rather 8-bit type sounds out of this. If we combine that with some other more interesting frequencies. You can get some really harsh sounds out of it. So that is the synthesizer we've got. Let's now look at the rest of the code that have made that happen. Here, as you see, we have our envelope code. We have our oscillator code, which hasn't changed. Well, a couple of slight changes. The main change I've added to it is a calculation from MIDI note to the frequency we need to play. So if you remember previously, we had a set freak function that called this freak to delta to work out what the delta is. We now also need to convert from MIDI note to the frequency in hertz. Now I found this formula online and I just adapted it, but you start off by declaring what the frequency of A is at 440 hertz, and then you say the frequency of the note is actually A divided by 32 multiplied by math to the power, this is the exponential function of 2 to the power of the MIDI note value minus 9 divided by 12. That's the standard mapping to get from MIDI note to hertz. Like a lot of things in musical notation, it might actually not be perfect, but it's a kind of approximation. It's a good enough approximation that people will use in synthesizers. And then once you've calculated that, you can just call the original set frequency again, which will convert that into the delta. And we also, every time the MIDI note goes down, we set the phase back to 0. That's just handy. It means that at the beginning of each new note, we're not halfway through the wave somewhere. We're going back to the beginning of the wave. In a square wave, it doesn't really make much difference. For if this was a sine wave or something, it would stop little sort of clicking and popping sounds. So that's the only thing that's new about the oscillators. We have this extra method for turning the MIDI note value into thing. And remember, the MIDI note encoding, that is, this series of numbers from 1 to 127 that represent the notes. This is an absolute standard everywhere, and of course all the DAWs will use this standard as well. So we still have our OSC1 and OSC2 as our two oscillators. However, we don't, if you remember, we set the frequency of them using this frequency ratio parameter. So if you look at the code here, we've created a variable called O12 ratio. That's just what's the number, we take whatever the frequency of oscillator 1 is, multiply it by this number to get the frequency we're going to give to oscillator 2. That's how we keep that ratio between them. The LFO works the same as before. And then here you see we're creating two envelopes. An envelope, a variable env, which contains our amplitude envelope, and that's giving our default values, ADSR. And then PWEnv, that's the envelope for our pulse width, which is also going to evolve following an envelope through the duration of the note. Now, process block, we have to add a bit more to it, because process block is now also going to get in the MIDI notes from that are being played, or from the piano roll or whatever. So we use a slightly different version of the process block. Process block is a method that can have two arguments, the samples and S max, as we saw previously, but there's also a version that receives as its third argument the MIDI buffer. The MIDI buffer is the MIDI notes that you get. If you remember the second tutorial on the arpeggiator, we were using this version to get the MIDI notes in. And rather like that, the first thing we do is we loop through that MIDI buffer to get all the events. But now it's fairly simple what we have to do with them. We just say if the event is a note on, well, we know what to do with a note on. We want to start our envelope at the beginning of the attack phase, the attack stage. So we get the value of the note. Remember, note is now that's that MIDI note value. And we set the oscillator MIDI note. We call the MIDI note of it to being that note. We now set oscillator 2, we set its frequency directly, not through MIDI, not through that note, but we set the frequency directly as being simply the frequency of oscillator 1, OSC1.freq, times that ratio variable we set up to be that. Finally, we send the note on message to the envelope. Now, if you remember, the note on message simply puts us at stage 0. So we're starting the attack stage. And that's all we do. Whenever we receive a note on in our MIDI buffer, we set the new frequency of oscillator 1, we set the new frequency of oscillator 2 as the frequency of oscillator 1 times that ratio. We set the envelope to start playing, and then we do the same for the pulse width envelope. We set that to start playing too. If the event is a note off event rather than note on, we just send the note off to both envelope and the pulse width envelope. We put those now into their stage 3 to start dying away. That's it. That's all we do with MIDI. Now here for the next part is the same, roughly the same thing we did in the previous one. Now the only thing that's new here is before we get the previous version, remember we got the values of V1 and V2, the volume of the oscillators, we added them together, then we modulated them based on the low frequency oscillator. Now we've got these envelopes, so the first thing we do is we actually get the new value. PW is a variable that gets the value, the next value from the pulse width envelope. Remember, that's also going from 0 up to 1 and then back, and having received that value, we now set the pulse width of both oscillator 1 and oscillator 2. So we don't have, at the moment, both oscillators have the same pulse width. Maybe that makes it a bit less interesting. We can experiment, but so far we just set the pulse width of oscillator 1 and oscillator 2 from that next value that came out of the pulse width envelope. Now we just call next again on oscillator 1 and 2. there's one extra stage. We're going to get all of these. This calculation here is is both of the oscillators as modulated by the low frequency oscillator. But now we just take that value and we multiply it by env next. In other words, we now multiply it by the volume, the next V coming out of our volume envelope. So that's what gives the whole overall sound is shaped by that. And that's it. That's what we've done to add an envelope, two envelopes in fact, both an amplitude envelope and an envelope controlling the pulse width to our synthesizer. Now, you can see we've changed the parameters a little bit. So, okay, the oscillator 1 and oscillator 2 amplitude are the same. The frequency ratio between the two, if you remember this third one here that controls the frequency ratio between the first and the second oscillator, that now updates this variable called 012 ratio, which you remember we declared here and which we use in order to calculate the new frequency of oscillator 2. So that's now being updated by that frequency ratio control. The envelope, attack, decay, sustain, you're all simply taking that value in and calling the appropriate set attack, set decay, set sustain, set release methods of our envelope object. Exactly the same for our pulse width envelope. We're just setting the attack and decay on the pulse width envelope object, and the low frequency oscillator does the same as it did before, I think. Yeah. So, okay, we really set this. Let's set this to 0.5. That's a reasonable sound. Let's pull down the LFO. Right, let's just see if we can what this pulse width envelope seems to do for us. Let's make it a very short attack and a short decay, and let's take the sustain down to nothing as well, so that we really have, we're going to have, now if we were to take the sustain of that up, in other words, from rather than most of its time hanging around at the low end, let's take it up to the high end. I'm simply tapping it as I change this. You can hear how it's affecting this attack and decay stages. Most of the interest actually is still happening really with the sustain, because that's the weird thing that's saying most of the time, are you more down at the 0, or are you more up at the 1, or are you kind of more in the middle somewhere? So if you hear, that's giving us most of our control. So possibly this is lost a little bit of its expressivity from the perspective of as a drone machine, and obviously you might prefer to keep using it as a drone machine, but as you can see, it is perfectly possible to make a very traditional ADSR envelope and some other fairly traditional things and use this, have this all working within this Lua VST. So just to demonstrate that, we can put this into the piano roll. You'll see we don't currently take any notice of the velocity information. That might be an interesting thing to do next, but it works as a synthesizer. Of course, it's a monophonic synthesizer. You can't play two notes at once. We could certainly add some effects to it, though. And we can always add a whole range of, to thicken the sound out with an overdrive, then smooth it a bit with some quite loud. So we have a perfectly workable functional synthesizer, and obviously if we want another one, we can add more. A second copy of the Protoplug here, and let's put in something more, take down perhaps the very harsh at the moment. Seeing if I can try to more or less sync the LFO with the actual speed of the music. Yeah, so it's a workable, usable synthesizer, even in that still very crude stage. So that's it really. I mean, I think there's the code will as always be available. It's still pretty short, as you can see. We are down at 150 lines, maybe no 200 and yeah, we're on almost 300 lines now. But it hopefully it is still pretty easy to understand. And as I say, get the code, have a look at it, see what you can do next in terms of making your own variants, etc. And well, okay, so there's one last thing I want to show you. Let's go back to these parameters here. You might feel that working with this interface is not the most beautiful interface, it's not the most convenient interface. As you can see, I occasionally kind of hit it and type something in and make a mistake. What's great in FL Studio, now everything I've shown you until now is should work in any DAW, right? I mean, Lua Protoplug, standard VST, should work anywhere. I'm a bit less sure about this in other DAWs, but what you can do, and I was quite surprised actually when I found this worked, is that we can actually create a control surface for this. So if I go to the control surface here, and I'm now going to add some knobs to it. This is obviously an FL Studio thing, black cog. Let's have one of those, and let's duplicate it, and let's duplicate it. And now let's say we'll rename this OS1 Vol. We'll rename this OS2 Vol, and we'll rename this one Ratio. And now if we come to here and we look at browse parameters, and you will see that those parameter names are available to us. So if we go to OS1 amplitude and we link to a controller, and you'll see surface OS1 volume is there, accept that connection. Come down here again, browse the parameters, OS2 amplitude, link to controller, OS2 volume, and now we'll do the same again here. Browse parameter, frequency ratio, link to controller, surface ratio. We now have, if you look at these options here, and you look now at our control surface, do we see, yeah, now you can see that the oscillator 1 volume does indeed control the oscillator 1 amplitude there, oscillator 2 does control that, and the ratio does that. So if we start playing again, the more we change that ratio, of course, let's just take the other one away for a second. When we change that ratio, we're going to get some out of tune stuff. But you can see that we are now able to play this in what's a pretty civilized way, right? I mean, these control surfaces are convenient. I mean, if you have an external controller with knobs on it, you can map those to these control surfaces. So this Lua Protoplug, it kind of looks perhaps a little bit crude on first glance at it, but you can make a working synthesizer with the stuff you want, and then in FL Studio at the very least, you can just make your own control panels, your control surfaces, and you can just play it like any other synth, any other VST in your thing. So I was impressed because I literally didn't know that was possible until I tried it yesterday, and I'm very happy that it works. And obviously this is much easier to work with than that. So once you've made a synthesizer, once you've made your own custom synth, make your own custom control surface as well. So that's it. That's today's tutorial, and I will probably do one more on this synthesizer in the not too distant future, and I will certainly do a lot more on Protoplug in the next couple of months, but we will certainly be doing a few other things as well. So thanks for watching, and I will see you in the next one. Oh, and if you like this stuff, subscribe, because it is, there's more and more good stuff on this channel. So, and I'm even, I don't know, you tell me if you think my recording technique is still a disaster or if I'm improving on that. But I think the content here is getting very interesting indeed. So, you should be subscribed.